All right, so now we're going to look at another application of the Newton's method for systems. Okay, so we're going to look at roots of a complex function. Okay, so let's look at this by example. So let's say I have a complex function f of z, which is 2z cubed plus 5z squared plus z plus 15. And I want to find, so this is a cubic polynomial. So it has 3 roots. And here I'm going to have that the I is the square root of minus 1. Okay, so we know that any complex number z can be written as the sum of a real and imaginary part. Okay, where x is the real part and y is the imaginary part. Okay, and in particular x and y are reals. Okay, so I'm going to rewrite this into the following. So the goal is to rewrite f of z, okay, as f of x plus iy, and I'm going to write this as some function a of xy plus I b of xy, where now a of xy and b of xy are real. Okay, all right, so that's basically what's going to happen. Then if you can do that, right, then f of z being 0 is equivalent to saying that a of xy equals to 0 and b of xy equals to 0. Okay, so I'm going to essentially rewrite this complex valued function, which depends on a complex number, as 2 real valued functions vanishing, so 2 real valued functions which depend on 2 real numbers. Okay. All right. So that's the plan of attack. So we have that function f of z. I'm going to write it as x plus iy. So this is 2 z cubed is x cubed plus 3i x squared y plus 3i squared y squared x plus I cubed y cubed, right, plus 5 x squared plus 2i xy plus I squared y squared plus x plus iy plus 15. And I'm going to use the fact that I squared equals to minus 1 to simplify these expressions. Okay, so this gives me 2x cubed plus 6i x squared y plus minus 6 y squared x minus 2i y cubed plus 5x squared, right, plus 10i xy minus 5y squared plus x plus iy plus 15 and I'm going to collect all the terms involving I, right? That gives me 2x cubed minus 6xy squared plus 5x squared minus 5y squared plus x plus 15, this is the real part, plus I times 6x squared y minus 2y cubed plus 10xy plus y. Okay. All right. So this, so I've rewritten f of z as, which is f of x plus iy as a xy plus I b of xy, where axy is this expression, right? 2x cubed minus 6 xy squared plus 5x squared minus 5y squared plus x plus 15, and b of xy is equal to 6x squared y minus 2y cubed plus 10xy plus y. Okay, and I need to solve for the simultaneous zeros of these two functions. Okay, and as before, if you wanted to apply Newton's method to this, you have to compute the Jacobian of this system of equations. So the Jacobian here, J, which depends on A and B, sorry, X and Y. Right, is the partial respect to A of X, partial respect to A, partial of A respect to Y, partial of B respect to X, partial of B respect to Y. And that is equal to, okay, so 12xy plus 10y. Sorry, looking at the wrong line. That's the one below. 12xy plus 10y. Okay, so A is this one, sorry. So differentiating partial respect to x is 6x squared minus 6y squared plus 10x plus 1. Okay, yes, and then I have to take a partial of this A respect to y. That's minus 12y, well, 12xy. And minus 10y. Okay, then I have to differentiate b respect to y. That's 6x squared minus 6y squared plus 10x plus 1. Okay. All right. So anyway, so now it's like if you're trying to find the roots of this sort of complex valued polynomial, it's like on the complex plane, you can then apply Newton's method to this. Okay. So I should say that I should make the following remark that when you try doing this, you can actually try to color the plane based on, so there, as I mentioned, it's like this complex, sorry, this cubic polynomial, it's like on the complex plane, it's like has 3 roots, right? So if you color, it's like the initial point based on which root it converges to, and you do this, it's like on the entire complex plane, then you get an interesting sort of fractal known as a Newton fractal. So just this idea of a Newton fractal. Okay, so that's something it's like I would encourage you to look up. What you'll see is that there's actually quite a lot of complexity. It's like in the the boundary between the domains of attraction of Newton's method. So the boundary, it's like between the basins of attraction actually ends up being very, very complicated and having a fractal type nature to it. So that's kind of an interesting thing to look up if you haven't seen it before. I strongly encourage you to do that. Yeah. So anyway, so let me just stop here for now.